heat pumps are widely held to be the main low carbon technology that will be deployed at a range of scales across the UK heat sector to help meet our climate change goals. Therefore, this week we look at the main principles to bear in mind when considering heat pumps for large heat networks, under what conditions they perform best, and some of the justifications for heat pumps vis-a-vis the alternatives. Star Renewable Energy has deployed large heat pumps here in the UK and abroad, and we have also collaborated with them on a heat network. And as such, we were keen that Dave Pearson expand on these questions. Dave, I'm going to pass you over the reins and let you take it from here. You got it?
Okay.
Great.
Right. Good morning. Thanks everyone for joining. It occurred to me during that introduction, it's almost a bit like being a gangster rapper. It's Dave Pearson in the house. Well, we're all in the house, so hopefully this is a good start to today's. We're facing another day in the house. But as I go back over 12 years, I ponder why we're doing this, and some of the conversations we've had. I see from the delegates list there's a few familiar names on there, and you know, all of these people have been quite inspiring over the piece. I suppose half the people I meet have tended to say, what is a heat pump? And so the first part of this will tackle what is a heat pump. The second half of the people I meet tend to say, yeah, but heat pumps don't work above 45 degrees. And so there's an element of, yes, they can work above 45 degrees. And I think we've moved over 12 years that I've been involved to where people generally do accept that heat pumps can reach the temperatures and they do work. The question is, how do you squeeze extra out of that heat pump? How do you make an average heat pump into a great heat pump? And the simple answer is the heat pump can't do that itself. It's all about the system design, but the heat pump has to be ready to work with a really dynamic and well-managed system. So we'll start off with the basic part of it. Just see if my click works here. No, we're stuck, Ben. It's not advancing this. Okay, so bit about Star Refrigeration. First of all, it's not a heat pump company in itself. It's actually a large industrial cooling company, over 50 years old this year. 364 staff now in the UK, but looking after large cold infrastructure. So interesting time for us, trying to keep all these food factories up and running in the distribution centres. We look after all of Tesco and Asda's logistics centres for them, so that's quite a challenge for us. Every frozen chip and fish finger and chilled for that matter is lands on us. But we got into heat pumps back, it says 2011 here, but it's actually 2008. I was Director of Innovation, thinking about what else we could do. And so we got into heat pumps because we recognised that there was a trend for sustainability. So very basic, first of all, what is a heat pump? It's essentially a refrigerator, the same as in your house. There's a cold bit and a warm bit, and we're cooling something down. In this example I've got here, it's an Airsource heat pump. So we're pulling air in and we're cooling it down to take the heat from it, the energy from it, and we are driving a compressor around a closed cycle driven by electricity. And that electricity plus the energy that we take out of the air, cooling it down by maybe 5 or 6 degrees, ends up as heat on the warm side at a higher temperature. So the air might only be, say, 5 degrees, but we're producing heat at 60 degrees for the useful purpose. The thing we tend to talk about quite a lot is the coefficient of performance, or you could say efficiency. I was lambasted in a previous thing for saying that we had an efficiency of 300%, and everybody jumped on me and said that's not possible. Well, I haven't yet found a way of saying precisely what we are doing, but in layman's terms, but coefficient of performance of 3 means we're getting 3 units of heat for 1 unit of electricity, and that's quite a good ratio when you think about it in whether it's cost terms or carbon terms. So the other aspect of what we do is river source heat pumps. Tend to find the larger systems a river source. There's some schemes in Scandinavia that are 160 megawatts in capacity, and they're absolutely gigantic compared to anything we've managed to do so far. Our largest that I'll come on to in Drammen in Norway is about 13 or 14 megawatts. So factors of 10 larger than what we're doing. But same principle, we're taking in something that we can cool down. So the river water on the left-hand side here typically ranges between 5 and 10 degrees. We drive the closed cycle refrigeration circuit and we produce heat in a ratio of about 3 to 1 again. In this case, we're producing heat at up to 80 degrees. So that's a good bit warmer than the 60 or so from the Airsource heat pump. So the science bit, any of you who studied thermodynamics will recognize this as a pH chart, but it's basically what governs the science of it. And as Scotty from Star Trek said, you can't change the laws of physics, which is true. You can't, but you can make them work to your advantage. So whereas heat recovery, which is very commonplace in many processes, is taking something warmer and allowing the heat to transfer to warm something cooler up, but not any higher than the thing we started with. Heat pumps are essentially, quite literally as the name says, we're pumping heat uphill. So just as a water pump pumps heat uphill, we're boosting heat in this cycle from round about 0 degrees. The thing we're cooling down is about 0 degrees, and we're raising that heat up to 80 degrees. So this line here, the sloping line, is the work line. This is where the electricity is going in. Line number 2 is the quantity of heat that we're getting out, and line number 4 is the quantity of cooling that we're doing. And the ratio should be roughly 3 to 1. So line number 2 is 3 times the length of line number 1, and line number 4 is 2 times the length of line number 1. So what we can do though is we can play around with what those temperatures are. If, for example, we fed in at 75, we would be putting less work in at line number 1, but getting roughly the same amount of heat out. Equally, if we raised line number 4 and found something warmer that we could cool down, we can do it better. However, it's not as simple as that, because that's essentially asking systems to change and be dynamic, which is sometimes possible. But what we're really looking for is how we recover the maximum amount of heat from this. So one thing that I find has made heat pumps very confusing to think about is that there's many different types of them, and they've all got a place. They wouldn't be getting produced by whoever the manufacturer is if they didn't have a space. So at the absolute extreme end of things, we've got industrial heat pumps, and in some cases we're now looking at raising heat at up to 150 degrees. And very much more commonplace is new domestic buildings. So we're seeing heat pumps being deployed in new Bovis or Cala housing estates that are being built, and that's great. And that's a very different heat pump from this industrial heat pump. In the existing domestic sector, so my house, it's a 1950s bungalow in the south side of Glasgow. I've got a heat pump and I'm managing to heat even my not terribly well insulated building, but using a heat pump that's now operating at a slightly higher temperature, typically between 50 and 55 with a ground source, and I'm able to heat my house even through the winter. I have no gas connection anymore whatsoever. And then there's the new urban area. So as we're building out new areas of cities, and this is the example that we're doing down at Queen's Quay, originally designed by Ramboll, and we're now adding to that with Vital Energy, and I'll talk a good bit more about that. But that's a new urban area where we're able to say to the buildings, this is the temperature you'll get your heat at. But the segment that we're most interested in, and really I implore everybody to think not about just the little bits that we can do, but the big bits. The entire city centre of Glasgow has to decarbonise. The entire city centre of whatever city you're in just now, whether it's Edinburgh or London or Manchester, we have to decarbonise the entirety of the city centre. And we believe that district heating is the way to bring those volumes, very significant volumes of heat in. And we believe that heat pumps are the way to produce the heat that's fed into the district heating. But we absolutely recognise, how do we do that better rather than not so good? So this particular segment is all about heat pumps for existing urban settings where we're going to connect all the buildings to decarbonise them all. So back to this river source heat pump in this particular case here that we're going to look at. So having said that, sorry, I'm getting my slides jumped about. We have produced an Airsource heat pump. This is for a site in the south side of Glasgow. The Airsource heat pump is characterised by the table here. So you can see if it's a 20-degree day outside in Glasgow, quite rare, those of you who know Glasgow, we'll get 570 kilowatts of heat. If it's a -10 day, also quite rare in Glasgow, we'll get 278. Typical temperature in Glasgow actually varies between 0 and 10 degrees, 10 degrees being about the middle. So we would say this is around about a 400 kilowatt heat pump. To put in context, one of the challenges, this smaller area down here is the gas boiler house, and there's actually about 1200 kilowatts of gas boilers in that box there. That is roughly about a third of the size of the heat pump bit. So heat pumps tend to be a bit bigger and chunkier, and that's just a fact of life. But what we're doing here is we're raising heat up to 60 degrees with these coefficients here. So you can see just in the small text, heating based on 40 to 60 with that inlet air temperature. And so you can see the COP, that the efficiency ratio varies from less than 2 to over 3. And that's using a HFC working fluid, cousins of CFC, and now being phased down. But when we conceived this project a few years ago, that was the gas that was felt to be best to use. And they all give you a slightly different efficiency effect. But so what we're getting is an efficiency ranging, typically over the season, it will be about 2.7 or so. So back to the larger water source. This is the schematic on the left in an actual picture. This was built 2011, and it's still the largest 90-degree ammonia heat pump in the world, and that's after 10 years. Plenty of bigger systems have been done at lower temperatures, but still at 90 degrees. And this was for retrofitting into an existing district heating scheme. So we were set the challenge, and it's all very well to say let's do stuff at lower temperatures, but if the buildings are all connected and need heat at, and it varies over the year, it's dynamically controlled, but from 75 to 90 at various times in the year. So this building here is where the heat pumps are. It's about 20 meters by 20 meters to give us about 14 megawatts of capacity. So as I said, it's still the largest in the world. It's quite a complicated scheme, and I won't get too much into this, but we're actually doing 2 stages of compression. So instead of having one sloping line to the right, we've broken that in 2 chunks. So we squash the gas and heat it, and then cool it back down again, and then squash it again, and that gives us more efficient compression. We've also got 3 heat pumps in series, so actually it's a 60 to 70 heat pump heating water, and then the water's heated from 70 to 80, and then it's heated from 80 to 90, and that gives us an average efficiency more akin to what we would get if it was only an 80-degree heat pump. So we've tricked the science, if you like, to get 90 degrees out from a heat pump that's got the efficiency of an 80-degree heat pump, and that's absolutely key. Heat pumps are a very honest device. You put electricity in and you get heat out, and the ratio comes down to how good a job you've done. So fairly large. This is either the best photo or the worst photo of the plant, but these are the motors. They reach around about 800 kilowatts, and they're so big that we water cooled them. The amount of waste heat from the motors would have been about 160 kilowatts. So that's 161 bar electric heaters worth of heat into the plant room if we hadn't used water cooled motors. So we actually collect the waste heat from the motors. They are high efficiency motors, about 97%, but still that energy, we want it back to feed back into the system and improve the efficiency. Queen's Quay is the project I mentioned earlier, originally designed by Ramboll. West Dunbartonshire Council and our client Vital Energy have done the detailed design for this, and that's down in Clydebank near Glasgow, just about there. And you see city centre of Glasgow here. The River Clyde runs all the way down here. I sat at an interesting seminar yesterday, and it was talking about solar heat, and it reminded me that the River Clyde drains an area of 4,000 square kilometres in the upper regions above Glasgow and Lanarkshire. And so effectively the River Clyde is part of a solar collection system, and then gravity brings the heat directly into where we want to harvest it. And that's just a lucky coincidence. So what are we actually seeing down there? Well, there's a site that's been cleared. It was the old John Brown shipyard. There's some existing stuff that's been built that will be connected. This is a college, and there's a new sports centre being built here. But this entire area in the red boundary is new housing, and there's a medical centre and some other community facilities, and that will all be connected to the district heating. The planners were able to say, yes, this is what we want you to do, so there isn't going to be a gas connection. Please use district heating from heat pumps. And they were able to say as well, we want district heating from heat pumps because we recognise that that's the right way to do it. So when it's finished, it will look a little bit like this, quite a fancy building that's going up. And there we are with the college next to it and there, and you can see the crane and all these houses. And it's a very short 20-minute train ride into Glasgow. So I think this is going to be quite an attractive place once it's all finished. So river temperature, why pick a river? Well, it's not the warmest thing that we could find. We could drill a hole in the ground and go much deeper and get heat at maybe somewhere between 20 and 40 degrees, but it's very, very predictable. It's also low cost. You can get the heat from the river without spending too much money. So what we're doing with the river is harnessing the fact that it's typically between 4 and 17 degrees all year, average temperature around about 10. And so we're taking that and cooling it down by about 2 or 3 Kelvin to give us that heat input into the heat pump. Pumping center next to the river, and energy center over here. Now, some people, when we start the conversation, say, well, I want to put a brake loop because I don't want my heat pumps touching the river water because that might damage them. And we try and point out that by putting a brake loop, you've got a 2 or 3 degree temperature difference. And what if you made a heat pump that was slightly better and was able to take that water directly into the heat pump? The impact we would get by having no brake loop is a heat pump that's operating 2 or 3 degrees warmer. Now, you might say 2 or 3 degrees, why bother? And that's the point of the next couple of slides, is to show why that's significant. So what we did was we built heat pumps with this tubular heat exchanger here. We call it a spray chiller. And in the bottom half, there's tubes that the river water passes through. They're made of titanium, so we're not worried about the corrosion of the tubes. And on the outside is the liquid ammonia that's being sprayed by the refrigeration system. We're also able to automatically clean the inside of the tubes. So why is 2 or 3 degrees worth having? So down the other end of the heat pumps, we've got the heat recovery part. So whilst the cold end, if you like, is quite important, the warm end is also, and you can see it looks quite busy. And the reason it's quite busy is because there's quite a few different places. So you can see up here is the desuperheater. So this is where we get the first chance to recover heat from the gas. Then still vapor, high pressure, goes across to the condenser, and we get probably about 80% of the heat out of the condenser, then into the subcooler. And also going on at the same time, we've got the oil cooler here, which is managing the oil temperature for the system to keep it running okay. So we'll pick through each of these and see why they're significant. So desuperheater, it's about 200 kilowatts out of 2,600. In terms of the condenser, it's about 1,800 out of the 2,600. So that's really the biggest chunk of the heat recovery. We can see in the subcooler, it's about 200 as well. And this is probably the one that features most in the next couple of slides as to why it's important. Obviously, we can adjust the temperature we flow forwards by managing the network better. But the biggest bit is if we can widen the delta of the network, we get a better efficiency. And that's really what we're trying to do here. And I'll try and show exactly why. But equally, oil cooler is about 600 kilowatts out of 2.6. So that's a big area of heat recovery. And we're able to get the heat out of the oil cooler at above the condensing temperature, because the gas going into the oil cooler the oil going into the oil cooler is around about 100 degrees. And that's really quite a rich grade of heat. So we're always trying to get stuff at the highest possible temperature that we can. So I mentioned about the river temperature and it varying, and this is just a very approximate chart. It's not necessarily for this site, but we can see that on some days, if we're taking the river water temperature at 5, we're able to get heat at about 3.15 efficiency. But if the river temperature is 10, then we're able to get it at 3.35. I did a quick calculation before I came on here. The guys in Drammen, if they vary their COP by about 10%, so that's varying from 3 down to 2.7, that will cost them £1.2 million over the life of the plant. So a very simple adjustment in COP equals a massive cost difference in the overall plant performance. The heat pumps in Drammen, incidentally, were probably around about £5 million, something like that. And so 1.2 million, that's probably about 25%. So by varying the COP by 10%, we've equaled the value of 25% of the overall project cost. Equally though, on the hot side, if we, instead of feeding out at 80 degrees, we can feed at 70 degrees, you can see we're changing the COP from about 2.6-ish up to about 3.4-ish. And that's a massive difference in value. So it's about helping the system operate at its absolute peak, and having the equipment there. If we hadn't installed a subcooler and we hadn't installed the ability to flex the condensing temperature, we wouldn't be able to offer these ongoing benefits. The great thing about a heat pump is you can install it and run it in one way, but a bit like a car where you're getting 30 miles per gallon because you're running around everywhere at 70 miles per hour. But if you start driving it better, you get better performance. This is all about how to drive your heat pump better. So you can see there's a little bit of complexity here, although compared to Dramin, it's much simpler. We've just got one heat pump in each circuit, and they're not interposing with each other. And we've got the subcooler getting the first chance to raise the temperature of the return water, and then the condenser, then the oil cooler, and the desuperheater. So that's the main bulk of it. In terms of the efficiency, we see, just to go back over, we see about a 1.5% efficiency change in terms of the forward temperature. So if we're flowing at 80, that's 1.5% worse than 79. And the delta on the network, if instead of being 20 Kelvin, we're 21 Kelvin, we'll be 0.5% better. And on the cold end of the system, if instead of being at 5 degrees, we're managing to use 6 degrees, we'll be about 1.5% better. So 1.5, 0.5, and 1.5 is the way that we're impacting the system by managing district heating better. So I think we've got some first initial questions, Ben.
Yes, indeed. Thanks very much for that, Dave. That was great. Now I can't see Finn. You want to stick on your webcam, Finn? There you go.
Yeah, so I'll wake up. Not that I was asleep, Dave, of course. So Dave, can you just tell us why why you think heat pumps are suitable in today's context for the built environment?
Yes, in Blue Peter fashion, I've prepared for these questions because I knew they were coming. But the first thing I'd like to say is, if the slide can just go forward again, I think we're just about getting past this. I think this why bother is how I would answer the first part of the question. If we change from burning gas to using heat pumps, we will increase our energy independence. We'll be giving cleaner air. We've seen that across the cities, that they've got much cleaner air with less transport at the moment. But still, if you look at any of the data, the NOx levels in cities haven't trended to zero. And of course, the transport hasn't trended to zero either. But even with 80% reduction in road transport in cities, we're still seeing NOx levels at about 40%. So that just sort of influences the thinking around air quality. Isn't just about transport, it's very much about other sources of NOx, and burning gas quite clearly is a source of NOx. There's no getting away from it. So we get into that area, and so we are potentially just creating a better world just for the fun of it. But actually, I think that's probably a good thing. But to answer the question more specifically about why heat pumps, and Ben, if you can just click me forward.
Yep.
So this is a graphic done by the European Heat Pump Association, and it's really the reasons for doing it. The first one, obviously, is the one everybody started talking about. These are blobs of ice cream, incidentally. The brown one there is greenhouse gas emissions. So if at Queen's Quay we're using electricity and it's got a carbon footprint per kilowatt hour of about, it's hard to say what the UK grid or Scottish grid, and you can get into incremental carbon factors, but it's round about 225, let's say. If we've got a ratio of 3 to 1, we'll be producing heat, and burning gas is a carbon footprint of about 225 grams per kilowatt hour as well by the time you get the boiler in efficiency. So you're getting a 67% saving in the carbon footprint. And of course, as the grid further decarbonizes, or you choose to run at certain times of day, the grid is better, you're lowering that. So this is trending towards zero. The second bit I've mentioned already is supply security. The UK now is importing more than half of the fossil fuel that it's using. And that's quite clearly putting a strain on the political aspects, but the economics of it totals something like £20 billion a year is being exported in cash to be swapped for fuel to come in that we burn mainly for heating. And obviously there's the local jobs, but energy efficiency is always important, and this drive for renewable down the end. But the one that I was really taken by, and we've not even got air quality on it, smart grids is a really important thing. This is basically saying if you can have dynamic customers, people that are able to switch on and off depending what the grid is doing, that helps. Now, there's one indisputable drive that's happening in the energy market, and that's offshore wind. We've found a way to do it cost effectively and cheaper every time, but it still has this intermittency, and it's far less intermittent when it's offshore and the towers are bigger, etc., etc. But having places like Clydebank that can agree to switch off and just use the thermal store helps balance the grid. The reason for doing it for the client is it's cheaper. Electricity varies on a half-hourly basis now, and so being smart grid compatible also means buying it at a better price. So I think there's a variety of things. I can't think of a heating technique that gives you all of these, including the air quality one, the seventh blob of ice cream. So that's why I think heat pumps are so pertinent. They're the only way to do all of these without completely wrecking the economy.
So what do you see as the barriers for heat pumps at the moment then, given that this is eminently the best way of doing things?
Partly awareness. I think also we, if you can click forward, Ben, please.
Yeah. After this question, Dave, we'll take a few questions from the audience.
Brilliant. I think indisputably cheap gas. We've got the cheapest gas in Europe. A report that came out fairly recently said that our gas is subsidised more than any other country in Europe. We've also got that very strong incentives, but I don't think people are confident enough to use them. So there's a whole thing around the costs. I think, and there's lots of different aspects of planning, but if you consider that it's easier to get planning permission to put a new gas pipe into a city than it is to put district heating pipe in, then you've got to come to the conclusion that that's clearly a bit counterintuitive to government policy. There's then some detailed stuff, and it's been rumbling around for a while, but non-domestic rates, essentially any building that's built as an energy centre will have to pay rates. And we nearly did a project in the centre of Glasgow in the Gorbals, and the rates cost for this was going to be about 50% of the value of the heat that we were producing. So we've got one government policy saying, please do clean heat, please move away from burning gas. And we've got another policy saying, but we're going to put a tax on top of that clean heat at 50%. That's just clearly not really very sensible. So I think we've got to sort these out. The Barclay review looked at it, and then they ducked the issue and said, we'll come back to that later. That frankly, is just not good enough. And then if you look at the progress in electricity and wind, there's one word missing from the heat sector, and that's obligation. All the buildings in the centre of a city, whether it's Aberdeen or whether it's Dundee or Glasgow or Edinburgh, they're not obligated to decarbonise. So we've also got this situation where we've got lots of district heating schemes, perhaps with gas CHP, and they're running along actually with a carbon footprint that's rising as the electricity grid decarbonises, but none of the buildings are obligated to do anything better. So I think when you take those four blobs there, they're probably the biggest areas. Each of them is very complicated within it, but I think fair to say lots of reasons. It's not that the technology doesn't work. That's the key thing. It's not that you can't make a financial model from this.
Okay, there's quite a few questions. I'll leave it to you two to decide whether some of these questions need to be perhaps discussed in more detail offline. But the first one from Callum: what are the main benefits to having a heat pump-led network as opposed to individual heat pumps for each building?
That's a really topical question. It's instead of having, and there's two ways of doing it. One is to have individual heat pumps for each building. The second is to have an ambient network where we're distributing 15-degree water around the community. I think it will come down to it's all better than gas. So doing any of these variants of the three variants is better than gas. But if you do centralized heat pumps, you've got all the maintenance in one place. You've also got a better ability to buy electricity at a cheap tariff. And about 75% of the life cycle cost of running a heat pump is the cost of electricity. And if you could buy that centrally at the right time of day, you've also got the notion, and there's quite clearly, and it depends, it goes back to the pie chart there and which segment we're in. If we're talking about the city centre of Glasgow, you couldn't put a heat pump in every building to decarbonise 100% for that. You can only do it with a large central heat pump. If we're talking about the suburbs, as I look out the window at the 1950s bungalows across the road from me, I don't think that's a district heating one. So depending which segment we're aiming at, one is right and the other is right for the other. But I think it comes down to just thinking about life cycle cost. It also comes down to consumer behavior, what's going to be easier for people to adopt or not adopt. So one for offline that I'm happy to discuss in more detail if Callum wants to get in touch.
Okay, I'm going to go to Roger asks sort of a number of questions which are sort of specific. How much does the superheater raise the delivered temperature, and how much does it reduce the overall kilowatt output? What is the output turn down ratio on the heat pump, and how efficient are high temperature heat networks? And he also asked,
so first one, we get about 1.5 degree uplift in our delivered temperature by using the superheater, the desuperheater, sorry. So it's definitely worth doing. It's a cost of metal, but it's saving energy over the piece. The second question was about the turn down ratio. There's always a penalty in terms of what the output is. So we can get to about 70% without much loss in efficiency. But if you went down to, which is perfectly feasible to run down at 30–40%, you'd probably have seen quite a big offset. My preferred way of doing it is to manage the network dynamically, and this draws into the Minibems skill set. But by using a thermal store, what you're able to do is run the heat pump for the shortest period possible at the maximum efficiency, buying the electricity at the cheapest. So fill the thermal store for 4 hours overnight with the heat pump running full load, and then switch it off during the day. That's probably how I'd run it, instead of running at say 25% all day long. And that's what our client in Norway does off peak. During the winter, they're running 99.5% of the winter full whack. But summertime, clearly less heat demand, they offload, but they do it on a stepped on-off profile. So it's a good question, but I think when you take the total economics, thermal stores are a good way of doing it. And the third question, Ben, was?
How efficient are high temperature heat networks?
It comes down to exactly what we've been talking about, source of heat and delivery of heat. We did some calculations, and if we were delivering heat at 120 degrees, but able to cool something from 80 down to 70, we'd have an efficiency of about 4:1. So that's even better than a 90-degree heat pump taking from a river. But think about the temperature difference. 0 river, 90-degree heat, that's a 90 Kelvin gap, but 70 to 120 is only about 50 Kelvin. So you get a slight improvement in the efficiency. So it's all about managing the entire temperature scheme around the whole bit.
Dave, what's the design temperature of Queen's Quay out of interest?
80.
80, so that's quite high, really, isn't it? Okay, so you're connecting up some old buildings, yeah. So at Minibems, we would say that typically with a radiator system, if you've got radiator systems in old buildings that were designed to 8271, let's say, in their day, we find that you can normally run those at about 15 or 20 degrees lower than the design temperature variably according to outside temperature. So that's where you get quite a significant benefit. If you're 1.5% less electricity for every degree that you drop that flow temperature, if you can dynamically run that heat network, variable temperature control all the radiator circuits and consequently all the and the primary network, then you could be dropping that flow temperature by as much as 10–15 degrees over the over the year.
And that's absolutely right. And from that statement of 15 degrees better, some days it might even be possible to even better still. If it's a fairly balmy 12 degrees, but you need a little bit of heating, then drop it another couple of degrees. And that's where the skills of Minibems really come in, is being able to predict, and not just that, but I guess also you can predict the heat demand of the properties as well, and start thinking about scheduling and when to run, and do I buy my electricity nighttime rather than daytime? And
yeah, so I mean, we're working on a new project within Innovate UK at the moment, which is to machine learn the heating curve of every heat consumer, so every apartment. And when I say the heating curve, I mean the what the flow temperature needs to be into the radiator system on every flat according to outside temperature. And so we're machine learning that on an individual heat consumer basis, apartment by apartment, because obviously every apartment will have a slightly different actual requirement, as in it will take a certain a certain amount of time to heat up the apartment given a set outside temperature and given a set given a set flow temperature. So if you can learn that, then you can optimize even further the variable temperature control into those apartments. Also, then what we can do is by learning the heat up time, the warm up time, and the cool down time, we can then start using that as a thermal battery. So the project within Inuit UK is called Buildings as Batteries, and it's about essentially using the heat network estate as a thermal battery, learning the thermal inertia of the buildings, building a thermal profile, and then using that profile to flexibly deliver heat, moving heat away from the peak times, taking advantage of negative electricity pricing. I thought it was really interesting what you said, that 75% of the cost of the heat pump is actually determined really by the price of electricity, not by the COP.
Yeah.
So if you can really move that.
Well, both together, the cost of the electricity, which is a function of the cost of making the heat.
Yeah.
So the operating of it. So a function of COP, but electricity is the big one. And it varies. You know, the best will in the world, if we're talking about electricity at 12p versus 7p overnight, you're not going to manage a heat pump better to the tune of an extra 50%. It's a real stretch. You know, we might get a bit on that, but running the system dynamically, and that's why what you're doing is so important, that you get the temperatures down. Ben, any questions relating to that or other completely different topics?
Listen, we're having quite a few questions come through. We've sort of got 5 more minutes of our sort of allotted time, but as long as you two are happy and those attendees are happy, we can sort of carry on with the questions.
Yeah,
sure. Yeah.
So just to sort of continue this, Roger's come back with a question regarding on the high heat network. And he says an 80-degree centigrade heat network is likely to have significant losses leading to inefficiency. And that was what he was talking about with the question regarding the efficiency of high temperature heat networks. I thought it was worth just maybe coming back to that.
Yeah, it does. You know, I remember having a conversation with one of the consultants, and he was saying 55-degree networks are better than 80-degree networks. And I said, I completely agree, but the university building, it was Glasgow University, its buildings were at that time needing 80-degree or maybe even slightly warmer heat. So you've got to design for what the building's doing. Now, of course, you can bring along more sophisticated design, but going to a grade A listed building and saying you've got to rip out all the internal pipework and all the radiators is a big step. I think the point is, though, if you put it in and it runs at 80 this year and you manage it the best you can, and maybe using something like Minibems, you get it down to 75 on many of the days, and it can flex back up to 80 for that one day of the year that's -3. But if at subsequent points they can do stuff to the buildings and get them down, then of course it gets better. And that's what I was saying about the beauty of a heat pump is you put it in and it's got an efficiency. You run it better, it's got a better efficiency. You adapt the building even further with more insulation or bigger radiators or whatever you do after the fact, and it gets better still. But if we wait for perfect before starting moving, I think it was a Churchill thing that perfect is the barrier of progress. We've got to get these things out there and in. And if we're you know, and again, Roger's point, I know Roger, and I know some of the stuff that they're doing. Quite often, what we're seeing is the majority of the activity in the UK is that different segment. It's about new areas or new buildings. So Roger's absolutely right. Designing a new building at 80 degrees is really stupid. I'll go as blunt as saying that. However, old buildings at the moment probably need something a bit closer to 80 until you start doing the clever stuff. So different segment on the pie piece as well is probably the polite way of saying we're both right.
I mean, we would say that 80 degrees is just your Christmas Day scenario anyway. It's a very small part of the year, and our data suggests that you can be running radiators that design for 80 at 60, 65 for a very large part of the heating season and still heat the building successfully. Yeah. So it is about that dynamic temperature control. Yeah.
Just related to this high temperature flow, there was another question that came in from Jonathan as to what you both think about the potential to supply older, higher temperature, 80-degree flow, 60-degree return, communal heating with heat pumps. Finn?
Yeah, I think that's a really big opportunity based on what I just said, really, just on, if you're able to dynamically control temperatures according to external, internal conditions and various factors, then certainly you can be picking up a significant amount of base load. We would normally find that we can get return temperatures off existing radiators down to about 35 degrees, as long as systems are balanced. So, you know, if you take the approach of rebalancing radiators, maybe having to change TRVs if you've got very poor TRVs, but if you can, you can typically get your radiator return temperature down to 35 degrees without too much work, and control to that temperature on the radiator system. You can then dynamically vary the flow temperature into those radiators according to various factors, and that then gives you thermal flexibility in the amount of thermal delivery, thermal power delivery that you've got going into the property according to real-time demand. And a lot of the time that can be, you know, again, those radiators can be running at 60, 65 degrees. You may still need some kind of redundancy, some kind of bivalent system that has a bit of higher temperature in it, or a heat pump that's designed to go up to a higher temperature. But, you know, if you're talking about small blocks, you might be looking at smaller heat pumps with you know, some top up from, you know, gas or something else for small parts of the year. But it, you know, if you look at degree day data, you know, I mean, we all know this. I mean, how often is it -7 in Glasgow, Dave? It's not very often, is it? But that's your design condition, isn't it, for Glasgow? It's what you'll be designing buildings for. Pardon?
Only in June.
Only in June, yeah. These days, yeah.
No, Glasgow's a fairly boring climate. But so does most of the UK, and it does in certain cases make it absolutely ideal for air source heat pumps, because, you know, the temperature of the air is never, you know, -7. So we're seeing some interesting stuff happening in the air source stuff as well. What other questions have you seen, Ben?
Yeah. So we've got another question about 5G networks, but I think we'll leave that one for the moment. It's a very interesting topic, probably worth a webinar itself. Carlos asks, do you see grid capacity constraints as the major challenge?
Yeah, I do, and if I can click forward in the slides, I've got something that speaks to this. Yeah, stop there. So one of the barriers, I talked about obligation, is that there isn't an obligation. So the heat networks bill that's coming through Scotland at the moment is going to say all buildings in a zone must connect to district heating, but it doesn't say that they must buy. And the reason that they won't buy is because they've still got a gas pipe, which is likely to be cheaper. So if we're going to say to people, please buy from district heating, and actually we're going to get a bit tougher on this, we're going to tell you that you're going to have to do this, or you're going to have to decarbonize or decrease the NOx emissions from the building in the city centre, we've got to get the best possible price. And Carlos alludes to two aspects here. The first one that he mentions is the actual grid constraint. You know, putting something like a series of 10 megawatt heat pumps down the banks of the River Clyde through the city centre of Glasgow probably stresses the grid. However, and it's maybe easier to conceive when we think of Edinburgh or Dundee, what if we had a series of offshore wind farms with a direct private cable to heat pumps sitting on barges next to the city? We would then be taking the electricity, and folk might know this or not, but the production cost of electricity and to get it on shore is round about 4.5 pence per kilowatt hour from offshore wind turbines. When you stick it in the grid and then pull it back out the grid 100 meters down the road, all of a sudden it's 10 pence per kilowatt hour, roughly. So what if we were taking our electricity direct private wire in this new constructed simple grid, because it's only hitting 4 or 5 points around the coast of Dundee or Aberdeen or wherever, then I think you overcome the point that Carlos was mentioning about, let's not stress out the grid that's there, but let's also think about the economics of power purchase. And actually, if you speak to people deploying offshore wind, they'll say the biggest challenge they've got at the moment is getting enough people to want to buy their electricity in a PPA. Personally, I think they need to start thinking about the customer as actual consumers of electricity rather than just this big autonomous grid that just exists all purveying and not thinking about who's actually paying for it. So good question from Carlos. I hope I've answered it. I see a move for direct private wire grids feeding heat networks and heat pumps.
You are seeing constraint on the other side of the equation, though, as well, Dave. I mean, we're speaking to a utility at the moment that's got a constrained wind problem. So, they don't have anywhere to put the oversupply of, or there's issues around oversupply of wind electricity. And so if you've got a smartly controlled heat network that you can use as a battery, then you can basically be putting that energy into the built environment as heat.
I mean, the thing about constraint periods is the electricity is not at a premium price during a constraint period. It's absolute rock bottom. In fact, in my house, for my domestic heat pump, I can buy negatively priced electricity at certain times of the day. If anyone wants an introduction fee for Octopus Energy at 50 quid each, happy to share the code. But I was buying electricity negatively, power washing my decking, charging my car, and running my heat pump one Sunday afternoon last week. So, we see these periods now. It's not always negative for sure, but just getting smart about the way stuff is moving around. And this is exactly why this topic is the key bit of using Minibems to predict the demand and modify the demand and predict the demand means you get a better outcome. We're talking about playing with the 70% chunk that's the life cycle cost of heat and squeezing that down, perhaps even by 50% if we get it all right. So it's the absolute key area going forwards. It's not about what the heat pump looks like. That's somewhat irrelevant. It's driving the whole system better.
Okay, listen, I think probably just one last question that once again I hope you guys can attend to. John is from a SAP assessment company, and some London developers are looking into ambient loop heat pumps. How does this vary to a standard heat pump network? Pros and cons. Maybe if both of you just give 1 or 2 points to that.
Ben, you go first.
I don't know the answer to that really. I don't know the economics. I've heard of developers looking at both options, i.e. low temperature and ambient loop, and costing out both, and finding that ULTHW is still coming out less expensive to build for the developer. That isn't to say that it's necessarily the cheapest OPEX over the year. I think that my personal view is that a lot of the ambient loop stuff has been driven by the RHI opportunity, and I don't know if you were to remove RHI whether it stands up against a heat pump with LTHW. I also think your point around Dave, your earlier point about having a single large heat pump where you can have an electricity contract on a half-hourly meter, which is very competitive, might if the electricity cost over the life cycle of the heat pump is the biggest determinant factor, then it's about getting that electricity cost down, isn't it? So if you can put that onto one grid connection, that probably is going to be the cheapest way of doing it, isn't it?
And
ignoring RHI, yeah.
Yeah, and there's several aspects to this. We're talking about a very sensible question that's got social aspects in its answer about what the consumer might want. And the consumer probably wants a plate heat exchanger HIU in their apartment, not a heat pump, when it all comes down to it. Accepting the other aspects, it's probably also answered by the political bit and what the rules say and what they don't say. There'll be economic bits. So if you're a developer and you're rolling out a network in phases, doing it with an ambient network is much easier because you're only putting pipes in and heat pump capacity as you go along that network. So there's definitely pros and cons. So when you do the matrix, you'll find out that there's a variety of different bits. I would answer the question slightly differently and say, I don't think the London plan is correct at the moment. It basically says 2 things rather than the third. It says join district heating if it's available. If it's not available, do your own super duper district heating system or a low carbon solution for those buildings. If you take a new development anywhere in a city and you make it standalone, not wider grid connected, you're actually making it harder to decarbonize the rest of that community. So if you take Oxford Street as an example, and you've got 100 buildings and there's a new one being built in the middle that will never buy heat from a wider district heating network, then you're making it harder for the other 99 buildings to obligate and join on district heating because you've got this gap site in the middle. So I don't think all these new developments should be making their own standalone thing, but the law's an ass, as they say. So I think we've got the policy wrong at the moment in the cities, and how we fix cities is not about fixing individual existing buildings or individual new heavy refurb buildings. It's about what is the best chance of fixing the entire city. If we get 30% decarbonisation of our cities, we might well not have bothered.
Okay, guys, listen, a number of people are sticking with us, but I think to wrap things up, unless there was any other points you wanted to go through.
I'm happy to take any emails from folk. I know a few folk on the list, but if they've got any questions, we've always tried to answer questions and help folk get their head around it. There isn't a single answer in most of these, but it's always a pleasure to try and answer people's questions.
Yes, please do, everybody. They're the details of us all. Please send anything that you want to discuss further to Dave or to Finian. You can get in touch with me mainly if you're interested in doing perhaps a webinar at some point in the future with us, or if you're looking for any other co-marketing opportunity.